Hello, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chatterjee. So in this class, we'll discuss about the pyramidal horn antenna. It is one of the most popular antennas for high gain applications. Gain usually is around 20 dBi. So in this discussion, we'll try to find a radiation pattern of the pyramidal horn antenna, far field radiation pattern of the pyramidal horn antenna. As you know that for any aperture antennas, there are three steps for finding the radiation patterns in the far field. The first step is you stabilize the fields inside the aperture. So the first step, we will try to stabilize the fields inside the aperture of the pyramidal horn antenna. Since you know that in the pyramidal horn antenna, you have flared out the open-ended rectangular waveguide in both x and y direction. So it is basically a combination of the E-plane and H-plane sectoral horn antennas. We have already discussed about the E-plane and H-plane sectoral horn antennas. So now, using those E-plane and H-plane sectoral horn antennas, we can make pyramidal horn antennas. Since we have flared out the open-ended rectangular waveguide in both x and y directions, we can write the aperture field variation of the pyramidal horn antenna as EAY E0 cosine of pi x dash by A. This is the amplitude variation of the aperture field. The phase variation, since you have flared out the open-ended waveguide in both x and y direction, the phase variation will have dependence, quadratic dependence with respect to x dash and y dash like this. So now the fields are stabilized in the aperture field. The next step is you have to find out the 2D Fourier transform. Just before that, let us look closely the amplitude and phase variation of the pyramidal horn antenna. The amplitude variation was E0 cos of pi x dash by A. So when x dash is 0, this will have maximum value E0, x dash is minus A by 2 or x dash is plus A by 2 at the two ends of the mouth of the horn antenna, you will have 0 electric field. So it has a cosine variation, maximum at the center of the mouth of the horn antenna and minimum at the two ends when x dash is equal to minus A by 2 and x dash is equal to plus A by 2. How about the phase variation? The phase variation now has both dependence with respect to x dash and y dash. So we need to see the phase variation with respect to x dash and y dash. So when x dash becomes y dash becomes 0, we are at the center of the mouth of the horn antenna. The phase becomes 1. It doesn't have any kind of changes in the phase, 0 phase change. But when you look at the two ends of the mouth of the horn antenna, y dash is equal to minus b by 2, x dash is equal to minus a by 2, or y dash is equal to b by 2 or x dash is equal to a by 2, you have the maximum phase variation at the two ends of the edges of the horn antenna. At the center, you don't have any phase variation. And it's just the opposite in case of amplitude variation. At the center, you have the maximum amplitude of the electric field, and at the two edges, you have 0 electric field. So let us go to the second step. In the second step, you find a 2D Fourier transform of the aperture field. All you need to do is multiply aperture field with the exponential minus exponential j beta x dash, exponential j beta y dash, and integrate over dx dash and dy dash. And the limit of integration will be from the minus a by 2 to plus a by 2, minus b by 2 to plus b by 2. Because fields are non-zero only inside the aperture, it's 0 outside the aperture. So now we can express, see, this is totally dependent on x dash, this is totally dependent on y dash. We can separate this integration and write this as E0, I2, I3. This is I2, this is I3. And you can find out this I2 and I3 by integrating this expression here, and it is given as half square root of pi r0 dash OH divided by beta, then exponential term here, exponential of j beta x1 square r0 h dash divided by 2 beta fs2 dash minus fs1 dash plus exponential j beta x2 square ROH dash divided by 2 beta ft2 dash minus ft1 dash. We have already defined what is this f function. We have also defined what is beta x1. So we can find the I2 from this expression. I3 can be also expressed as square root of pi r 0 e dash divided by beta exponential j beta y square r o e dash divided by 2 beta fs4 dash minus fs3 dash. We have already defined what is s4 dash s3 dash beta y. Then you can find out I2 and I3, and similarly you can find the 2D Fourier transform of the aperture field. Once you have the 2D Fourier transform of the aperture field, we'll go to the third step. Use equation 27.1 and 27.2 to find the far field electric fields of the pyramidal horn antenna. And it will have theta and phi component. It has a term which is same for both 27.1 and 0.2. They are very similar, except that in the first case you have sine phi here, you have cosine phi here. You also have 1 plus cos of theta aberration, and this is a 2D Fourier transform of the aperture field, where your 2D Fourier transform of the aperture field can be expressed as E naught I2 I3. I2 and I3 we have just discussed now. As usual, we are interested in the two principal planes. One is the E plane pattern, another is H plane pattern. And you know that E plane is when phi is equal to pi by 2. When phi is equal to pi by 2, sine of pi by 2 becomes 1. So we have only theta component. Cos of pi by 2 becomes 0, phi component 0. So we are interested only in the theta component of the electric field in the E plane pattern, because phi component is already 0. And substituting the variable mu is equal to sine theta sine phi. So sine of pi by 2 is 1, so it becomes sine theta beta x becomes 0, because cos of pi by 2 is 0. So beta x becomes 0. In that case, what you can observe is that beta x1 is beta x plus pi by a, becomes simply pi by a. Beta x2 is beta x minus pi by a, is equal to minus pi by a. So now what you can observe is this exponential term here and this exponential term here are independent of theta. So these terms are independent of theta. Let us see whether these terms are dependent on theta. S1 dash was defined like this, and S2 dash is also defined like this. T1 dash and T2 dash are defined respectively. So now here your beta x1 will become simply pi by a, beta here also pi by a, beta x2 becomes minus pi by a, so minus minus plus here, minus minus plus here. So what you can observe is that S1 dash, S2 dash, T1 dash, T2 dash are independent of theta. So in that case, the expression you have for I2 will be totally independent of theta. So it will not contribute in the normalized radiation pattern of the horn antenna, pyramidal horn antenna. Only the amplitude contribution will be there, but the variation with respect to theta is not there, because these terms are independent of theta. Let us look at the I3. I3 has a term like fs4 dash, fs3 dash, and you also see exponential term here. Beta y will become beta sine theta sine phi. Sine of pi by 2 is 1, so beta sine of theta. So this exponential term is dependent on theta. And we can also look at the expression for s3 dash and s4 dash, and it turns out to be dependent on theta. Here you have a sine theta term here, sine theta term here. So fs4 dash and fs3 dash are dependent on theta. Even this term is dependent on theta. So these terms I3 will actually decide the radiation pattern of the normalized radiation pattern of the pyramidal horn antenna for the E plane. So we can write the electric field in the far field, theta component, phi components anyway 0, is like this: j beta exponential minus j beta r divided by 4 pi r E naught I2. I2 is independent of theta, 1 plus cos theta I3. So this term will decide the normalized radiation pattern of the pyramidal horn antenna. Let us look at the H-plane patterns. When phi equal to 0, E theta component will be 0, E phi component would be like this. And let us look at the parameters beta y. Beta y will again now becomes 0, beta x will be beta sine theta, because phi is 0. So sine of phi, when phi is equal to 0 is 0. Cos of phi when phi is equal to 0 is 1. So beta y now will become 0, beta x will become beta sine theta. So let's look at the I2. I2 has exponential term, then this f function here. So beta x1 will become now beta sine theta plus pi by 2. Beta x2 will become beta sine theta minus pi by 2. So in that case, these exponential terms are dependent on theta now. This exponential term is also dependent on theta. How about this S21, S1 dash, S2 dash, S1 dash, T2 dash and T1 dash. Since beta x1, beta x2 are dependent on theta, these terms are also dependent on theta. Hence, I2 is totally dependent on theta. This will also help in the normalized radiation pattern plot of the I-plane, plot of the pyramidal horn antenna. And it can be observed that this radiation pattern in the far field for the I-plane is very much similar to the I-plane sectoral horn antenna. How about the I3? Let's look at the I3 dependence on theta. I3 beta y is 0. So this term, exponential term, will become 1 here. So it should be 1 here. Then this S4 dash and S3 dash. And since your sine theta, sine phi is 0, mu is 0. So it is independent of theta here. It's also independent of theta here. So I3 will be 2f S4 dash, and I3 is totally independent of theta. So I3 will not contribute anything in the far field radiation pattern, normalized radiation pattern of the horn antenna. Only I2 will contribute for the I-plane radiation pattern of the pyramidal horn antenna. So what we can see is that the phi component of the electric field in the far field for the I-plane radiation pattern of the pyramidal horn antenna will be decided by 1 plus cosine of theta I2. And it can be observed that this E-plane radiation pattern is this I-plane radiation pattern is very similar to the I-plane radiation pattern of I-plane sectoral horn antenna. And you can also observe that you can actually plot this radiation pattern and observe that E-plane radiation pattern is very similar to the E-plane radiation pattern of the E-plane sectoral horn antenna. So we are designing this horn antenna to improve the directivity of the open-ended waveguide. And so basically gain is a very important parameter for the pyramidal horn antenna. So we have actually changed the open-ended waveguide by flaring it out to make the pyramidal horn antenna to improve the gain of the horn antenna. So gain becomes a very important parameter for the horn antenna. Usually gain and the directivity of the horn antenna is very similar because horn antenna has very low losses. So we actually treat this directivity. You know that gain is equal to efficiency into directivity, but efficiency is very high, so directivity can be almost equivalent to the gain of the pyramidal horn antenna. That's why I have written gain of pyramidal horn antenna, and it can be found out from the directivity of the pyramidal horn antenna. So this is the standard expression you have for the gain of the pyramidal horn antenna. It's 4 pi by lambda square aperture efficiency A into B. A and B are dimensions of the horn antenna. So now this aperture efficiency now will have 3 terms, one due to the taper, cosine taper, one due to the phase changes in the E plane and phase changes in the S plane. So you are actually flaring out the open-ended rectangular waveguide to form the pyramidal horn antenna in both X and Y plane, Y direction. So because of that, there will be phase variation along X and Y. So that phase variation will calculate it. We also know what is the taper efficiency. Because of the cosine taper is 0.81, 8 by pi square. We can also find out the phase efficiency for optimum gain sectoral horn antenna, and you know that for the optimum gain sectoral horn antenna, the S parameter was 0.25 and T parameter was 0.375. So from there you can find out what is the E plane phase variation efficiency. It turns out to be 0.8, and S plane phase variation turns out to be 0.79. So this phase variation efficiency, when you multiply with this and this and this, final combined aperture efficiency of the pyramidal horn antenna is 0.51. So aperture efficiency is very low, 0.51. So the gain or directivity of the horn antenna is 0.51. 4 pi by lambda square a into b. A and b are dimensions of the pyramidal horn antenna. See, basically, as an antenna engineer, you're supposed to design a horn antenna for a specified gain. No? That's a usual problem you have. As an antenna engineer, you'll be given a specification on the gain of the horn antenna. You are supposed to design the dimensions of the horn antenna and fabricate and test its performance. So that's one of the problem we'll consider for the next slide. Just before that, let us try to find out some relations which would be required for designing the pyramidal horn antenna for a specified gain. So you already know that E-plane and H-plane sectoral horn antennas together make pyramidal horn antenna. So in order to make this pyramidal horn antenna physically realizable, the condition for physical realizability of the pyramidal horn antenna is that Re should be equal to Rs. Re is the E-plane side distance between the neck and the mouth of the horn antenna in the E-plane, and Rs is the distance between the neck and mouth of the horn antenna for the H-plane. So these two should be equal, otherwise you won't be able to make it. You won't be able to connect it to a waveguide properly, fit waveguide properly. So now this is the condition for physical realizability for the pyramidal horn antenna. Re should be equal to Rs. This is the distance between the neck and mouth of the horn antenna in E-plane and H-plane. Let us try to find out some geometric relations here. Look at this diagram here. This is for the E-plane sectoral horn antenna. You can see two triangles here. One triangle is O dash E. This triangle here. O dash E. This triangle here. Let us consider another triangle which is M O dash N. This triangle here. What you can see this is that these two are similar triangles. All the angles are equal. No? Angles of this triangle O dash E and the angle of this triangle M O dash N, all the angles are equal, so they are similar triangles. In that case, the ratio of the sides should be equal. For example, you take the ratio of O dash by O dash divided by M O dash, it should be equal to O dash E divided by O dash N. So this ratio of the sides should be equal. This is a property of similar triangles. So O dash means what? O dash is your R naught dash. Then M O dash is Re. O dash E is B by 2. And Re, this O dash N is basically capital B by 2 minus small b by 2. To simplify it, it becomes capital B divided by capital B minus B. So this is one relation. For the E-plane sectoral horn antenna, you can also have similar kind of relation by doing the similar kind of analysis. You can find out the ratio of Ro dash divided by Rh equal to capital A by capital A minus A. So now using these two relations, we will try to develop an equation for finding out the dimensions of the pyramidal horn antenna when the gain of the horn antenna is given. You know that Ro dash by Re is equal to capital B minus B. This is the relation we have just derived. Now this relation here, Ro dash divided by Re is equal to capital B minus divided by capital B minus B. Using this relation, also you know that for E-plane sectoral horn, optimum gain is achieved when B becomes square root of 2 lambda R naught dash. So what is this R naught dash? This R naught dash, you can get it from here, is Re capital B divided by capital B minus B. So you just replace it and you have square root of b here, you have b here, you take this to the left hand side in the denominator, divide it, you get square root of b. So square root of b is equal to 2 lambda re divided by capital B minus b. So you take square of this, you get capital B is equal to 2 lambda re by capital B minus b. You multiply this and it will turn out to be a quadratic equation in capital B. Capital B square minus b small b capital B minus 2 lambda re is equal to 0. So this is a quadratic equation in the capital B. We also have that for the H-plane sectoral horn antenna, Rs can be found out as capital A minus A divided by capital I R naught dash. And what is the optimum gain? For the optimum gain, what is the value of A? A was square root of 3 lambda R naught dash. So you plot the gain with respect to A and you find out what is the optimum value of the gain. And it turns out to be square root of 3 lambda R naught dash. And from here you can find out R naught dash is A square by 3 lambda. And you also have Rs is equal to capital A minus A divided by capital A R naught dash. Just replace this R naught dash as A square by 3 lambda here. What do you get? Rs is equal to this and this cancel out. So Rs is equal to capital A minus A divided by 3 lambda capital A. So now what was the quadratic equation of B, capital B? It was b square minus b minus 2 lambda re here. And you know that for horn antenna, pyramidal horn antenna to be physically realizable, re is equal to rs. So let us replace this re by rs. So rs is this here. Again you replace this rs here by this expression you have here and simplify it. Finally what you are getting is equation like a square minus a capital A square minus small a capital A minus 3 by 2 b square plus 3 by 2 small b into capital B is equal to 0. This is the equation you have here. So now we can further simplify this equation. You know that gain of the pyramidal horn antenna is epsilon aperture efficiency into 4 pi by lambda square a into b. So from here you for a specified gain you can either find a or b. So let's say I find b from this specified gain, then b will become g lambda square by 4 pi epsilon aperture into capital A. And from this value of b, from the specified gain, I can replace this capital B expression in this equation here. So now you have a square capital A square minus small a capital A minus 3 by 2. This was the b square. So we replace it by this expression 3 by 2 small b. This is capital B here. We replace by this expression. Finally, this is the equation you have here. And finally, the equation we simplified a square here, multiply everywhere. So what you are getting is 4 other equation in capital A. So capital A to the power 4 minus a capital A cube plus this term here capital A minus this term here is equal to 0. See, this is the 4th order equation in capital A. From here we can find out what is the value of capital A. We have already found out the value of capital B. Once we have the value of capital A, we can always find out the value of capital B from this relation here. I know what is gain, I know what is lambda operating wavelength, I know what is aperture efficiency 0.51. Once I have this capital A here, I can also find capital B. So that's how I can decide the dimension of the pyramidal horn antenna for the specified gain. But how do I get the value of capital A from here? See, basically in the book, which are usually quite old, they have given the process for finding this capital A in an iterative manner or by plotting graphs or doing a lot of calculations by plotting graphs or by doing iteration starting with the initial value. You keep on finding the value of A, and whenever it converges you find the value of A. So it takes a lot of time. Plotting the graph and iterative methods takes a lot of time, but nowadays you have very powerful softwares like MATLAB, and MATLAB you can easily do this actually. you can easily find the roots of this polynomial equation here. This polynomial equation here is of order 4. So you use the command roots command in MATLAB. When you use the root command in MATLAB, since this is of polynomial of order 4, you will have 4 roots. This is the first root, second root, third root, and fourth root. Note that we are doing it for X-band waveguide, where A is 22.86 millimeter, B is 10.16 millimeter, and I have assumed that gain is 10 dBi. You can assume it 20 dBi also. And aperture efficiency is, we have already derived, it is 0.51, and we are assuming the operating frequency is around 10 GHz. So the operating wavelength will be lambda. You plug in all those values here, then you will just get a fourth order equation in A with some coefficients here, which can be calculated from these values which are given here. Then you can use the roots command in MATLAB. It will give you 3 roots. And what are we trying to find? We are trying to find the value of capital A. Capital A is a dimension of the pyramidal horn antenna, and obviously this capital A cannot have complex values. So second and third roots are ruled out. It's not possible. The last one is also ruled out because we cannot have the length A as negative. So the only solution you have, possible solution, is this first solution, 44.9088 millimeter. So we have the value of capital A. So once we have the value of capital A, I can find capital B from this relation. I know what is gain, I know what is lambda. Lambda for this case is 30, gain is 10, absolute value is also 10, dBi is 10, so absolute value is also 10, epsilon aperture is 0.51, capital A is here, so I can find out capital B is 31.27 millimeter. So I have the value of A and B. So I have the dimension of the aperture of the pyramidal horn antenna, but we need to check one more thing, is that what is the condition for realizability, practical realizability for the pyramidal horn antenna? I have already told you Re should be equal to Rs. After taking this value of A and B, we need to verify that I should get Re is equal to Rs, otherwise this horn antenna is not realizable. So in order to check that, B is square root of 2 lambda R naught dash. This is for the optimal gain. What should the value of B? Square root of 2 lambda R naught dash. So R naught dash for this case, you know what is B, what is lambda. It turns out to be 16.29 millimeter. So once you have the RO dash, you can find out what is LE. LE is B squared by 4 plus R naught dash whole square. What was B? It's already calculated. R naught dash is also calculated. LE turned out to be 22.579 millimeter. Once I have the flaring length, I can find out what is the distance between the neck and mouth of the horn antenna for the E-plane as capital B minus B square root of LE by capital B whole square minus 1 by 4, and it turns out to be 10.997 millimeter. We can also calculate this for the I-plane case. For the I-plane sectoral horn antenna, the optimal value of A for the optimal gain was square root of 3 lambda R naught dash. It is square root of 2 lambda R naught dash here, but here it is square root of 3 lambda R naught dash. You need to keep that point in mind. So R naught dash for this case is A square by 3 lambda. It's 22.409 millimeter. So now you can find out flaring length in the H-plane as A square by 4 plus R naught dash square turns out to be 31.723 millimeter. So you can find out the distance between the neck and mouth for the H-plane turns out to be capital A minus A, the square root of LS by capital A whole square minus 1 by 4, and RS turns out to be 11 millimeter. What you can see is that RE and RS is same, almost same. So this pyramidal horn antenna we have designed is physically realizable. That's how you design the pyramidal horn antenna in the lab. That's all for the horn antennas. The next topic of discussion will be on the reflector antennas. The major problem with the horn antenna is that we cannot realize gain of order, let's say, above 30 dBi. Nowadays, for long distance communication, you need to have higher and higher gain for the antennas. So for that, we need to have some new types of antennas which are called reflector antennas. For example, you must have seen your TV antennas, DTH, direct to home TV antennas, you fit it on your rooftop, will have big one, parabolic in shape, and it is used for long distance communication like satellite communication. So those kind of antennas can give gain of order which is greater than 30 dBi. So we'll explore those kind of antennas in the next class. Thanks for your attention.